40th, I give the progress at 2, 21st progress at 3, and on December 9th, you're having in progress at 4. On the 21st of November, you get the last progress set due on December 9th when we meet for the question session.
Okay.
Now let's do a couple of examples with these externalities, which like how do exercises of this look like. So we have one consumer, 2 firms, and 2 goods and services. We will have some reduction externality. Example. Yes, please. It's a good idea. We have consumer, there's one consumer. With this conductor's utility function. Then we have firm A. Firm A produces good 1 from good 2. Which will be the consumption with X1 for the consumer from good 2. According to the function y8, y1a. A from base production, where we take into account that these are negative for whatever reason, because in the first order condition it comes out good as a negative. FA is the production minus y2a. And from B, and here's the externality. Produces with 2. X2. From good 1. We get y2b. And into fb minus y1b. Into minus y1b square root. Set of y1b plus x1. So this is where the externality comes from. Both the production and consumption of good 1 here impose the negative externality in the production of firm 2's output. So it reduces the production of firm 2. Then the consumer owns both firms, so this is the externality here, which reduces the output of the firm. And this minuses in front of here, it's like this production a la Pastel, but it's confusing, but later on you will see it with this. Okay, the consumer owns both firms, this is the usual thing. Endowment. It will be omega 1 is 1, and omega 2 is 1. So if 1 you will put 1 and put 2, which is an cells to the firm, you reduce this consumption good, these are the inputs. So let's see, A, because of the externality, the market equilibrium, the variation equilibrium in general will not be very efficient. So the first thing you do is find the very efficient outcome. The social element can derive, for example, so conditions for very efficient. So what do we doing here? Well, we maximize the utility of the consumer, and all the other things become constraints. X1 is equal to omega 1 plus y1a plus y1b, and here we see y is negative, the production functions, because if it's used as an output, it will be positive. If it is used as an input, it will be negative. It will take away from this right-hand side. Okay? So this is why these negative production functions make sense. Because here, this is produced as an output by term A, but when one is used as an input by term B, so this part will be negative. Then we have x2. Output produced by term B is equal to 2, but term A uses it as input, and then it's production. Y1A is minus Y2A square root, and Y2A is Y2B. Y2B is minus Y1B square root. Set times y1a plus x1. There's 4 constraints. So I will reduce this to 2 constraints by plugging the production functions into the budget constraints, into these market clearing conditions for the resources. And we can also write this as equivalently max, and now I write subject to, and then we get the first constraint is x1 minus omega 1. I put it all on the left hand side, this is 0. Then we get minus y1a on the left hand side, and y1a is minus y2a, so it's minus becomes positive, plus y2a squared, a squared. This one, x1 is consumed, is produced, minus y1 input of term equal to 0. And x2 minus w2 plus y1b square root, so I guess the first equation. But now we have the minus, and then we have this set, which also becomes a plus. But if we plug in for y1a this one, it becomes again a minus. It's a minus because it goes to the left hand side. It becomes a plus because of the minus here. But if you plug in for y1a, it becomes again a minus because of this one. It's a minus set y2a square root plus set x1 minus y2a equals 0. This is number 1. This is number 2. Now we derive the first conditions. Any questions about the constraints or these? It's a bit confusing with the minuses and everything, but it should be correct. I see this question.
Marcus, maybe this is a silly question, but what did you say Z was?
What is C?
Z.
Set.
Well, yeah,
Yeah.
Z.
C or set, what is like this, how much it's not a function, but it's a parameter. How much this affects the magnitude of the negative impact of the externality on the production of
Okay, so it's the magnitude of the externality.
The set is larger, it's larger magnitude, the set is smaller.
If we were seeing positive externalities, it would be a positive.
It would be plus set. Yeah, so positive production externality, you have the guy who has bees with the honey, and the guy who has the flowers. So
the flowers would be pollinize the flowers, yeah. Micro one.
Thanks for the time.
Yeah.
Good. First order conditions from Lagrange. So you write down the Lagrange, get the first order conditions, and how do they look like? Lagrange with respect to x1. So what is chosen? Consumer chooses x1 and x2. Firm A chooses how much input y2A to use, and firm B chooses how much input y1B. Firm A produces good 1 from good 2. This y2A is chosen by firm A, and y1B is input of firm B. How much good 1 we use to produce output 2. Lagrange with respect to x1. 1/4 x1 derivative is standard compactness condition plus lambda 1, because x1 is here in here, and x1 is again in here. It's plus lambda 2 set. Equal to 0. With respect to x2. The first part is again standard compactness. 1/4 plus, and so there's no externality here, so this only appears here with x2. And these are the consumption first order conditions for the consumer. Now, production first order conditions for
That's
firm A.
lambda 1 plus lambda 2c.
Yeah. Y2A, it doesn't appear in the objective function, but in the constraints. Remember, y2A was first in the first one, and it was in the second. In the first one is positive, so we have lambda 1 times 1/2 y2A minus 1/2 elevated to minus 1/2, and then we have minus lambda 2 with the c set. 1/2 times y2A minus 1/2 and minus lambda 2 equal to 0. Because it appears here as well. This will be equation 3. So with the last condition, Lagrange with respect to y1b minus lambda 1 plus lambda 2 1/2. Y1b minus 1/2 equal to 0. And this is the fourth condition. The fourth condition basically I rewrite as lambda 1 over lambda 2, so we get a ratio. There is minus lambda 1, we put it to the other side is positive. Divide by lambda 2, and this is equal to 1/2 y1b over minus 1. Related to y minus 1. Good. This is the fourth condition. Then you put together conditions 1 and 2. There's the usual marginal rate substitution condition, which is 1 divided by 2. This is 1/3. x2 over x1. Equal to, and here we have lambda 1 plus lambda 2 set. And here we have lambda 2. Lambda 1 over lambda 2. And this one plus lambda 2 over lambda 2 times set. So the lambda 2 you cancel it out, and we have set left. And then we get from 3, equation 3. What we do is, we get lambda 1, 1/2 of 2a elevated to minus 1/2. This first part here is equal to this part here. Set 1/2 by 2a elevated to minus 1/2 plus 1. Then we get lambda 1 over lambda 2. We're done basically. Lambda 1 over lambda 2. We get the conditions, which are this one, okay? Which is set 1/2 y to a elevated to minus 1/2 plus 1 divided by 1/2 y to a elevated to minus 1/2. Okay? That's solving for lambda 1 over lambda 2. And this is equal because the first part here cancels out to set plus, then we have 1 divided by this. We can flip it with the inverse fraction and we get this one. And then we are done. So lambda 1 over lambda 2 is an emission covariant efficiency. Will be lambda 1 over lambda 2. 1/2 y1b elevated to minus 1/2 from here. Here I put the set to the other side. I get 1/3 x2 over x1. And the set, and the third one is this one here, which is set plus 2 y to a elevated to 1/2 square root. Okay, so this we will keep. We will then compare it to the market solution and see obviously that if we don't have a market for the externality, the market solution will be different from this outcome, which is the efficient one. So this is the efficient outcome we just calculated, and now we go for the market solution. Without any tax or any assignment of property rights, so we see that we get a different solution. But how it compares to this. Okay, competitive equilibrium. So consumer. Consumer maximizes utility. What we get is marginal rate of substitution, MRS, equal to 1/3 x2 over x1 equal to p1, p2. Okay? And this is, well, very similar to what we get here. Just that this set makes this smaller. Okay? Fermi. Maximize profits. Maximize P1, Y1A. And the prices here are these shadow values of the constraint, so lambdas implicitly reflect the prices of the goods in the market. Y2A, subject 2, Y1A is the production function, minus Y2A elevated to 1/2. Plug this into the profits, the constraint, and maximize for Y2A. The input choice of the consumer, P1 times minus Y2A squared plus P2 Y2A. Therefore, C is minus P1 1/2 Y2A elevated to minus 1/2 plus P2 equal to 0. You solve for P1 over P2. And this is equal to P1 on the other side, divided by P2. Then there is this here, and again you multiply with the inverse fraction. So you get
minus P1 raised to 1/2 or times.
times calculated. Also in front more in P1 over P2 is 1 divided by this here, because here goes the other side, so we have to put it down. P2 goes here. So here we get the 2 y2a elevated to 1/2, the square root. And again, this is very similar to what we got here, but here we have the set. So, you see again, it's similar solution, but without the set. Then the last one. From B, maximize profit. P2, y to B, P1, y1b, and again the input will be negative. Subject 2, the production function, minus y1b square root, minus 7 times y1a plus x1, and so we get max y1b P2 minus y1b elevated to half minus z1, so I plug this production function in for y to b y1a plus x1 plus p1 y1b. And now I maximize with respect to y1b, the input choice of firm 2, and you get a first order condition, which is minus p2 1/2 times y1b elevated to minus 1/2 plus p1 equal to 0. And now when you get p1 over p2, unsurprisingly, with the y. P1 over p2 1/2 y1b elevated to minus 1/2. So what we get is the same condition as before, but without the set. The only condition which is the same, which is identical, is the one for firm B, which produces good 2 from input 1. And this is the same because firm 2 doesn't exert any negative externality on firm B, or firm A doesn't exert any negative externality. So this is not the optimal solution in the market. It's the same as from the social plan, because firm B doesn't exert any negative externality, so it's the same. For the two others, the consumer and the firm A, we have a difference between the optimal solution in the market and the volume efficient solution. Namely, here, what does this mean? Here we subtract, which basically, if you plug it to the other side, artificially you increase the price of good 1, which means that you should consume less. You make good 1 more expensive, you should consume less of good 1. Same thing here for the consumer. So this is this, so you see, you can do this, set up the problem with this social planner. You have 1 consumer, 2 firms, which is complex, it's strangely written with the minuses, but if you solve it, you come to the solution. And then you see, well, you get the same conditions in the market outcome and in the social planner outcome, but for this negative externality set, which is not present in the market outcome, if you don't take into account the externality. Let's do another example now with a positive externality.
Marcus,
Easier.
can you repeat again what you said? So the social planner and the markets arrive to the same and to what? To the
Well,
same
the solution is the same, but for the externality. So the first order conditions here, the P1 over P2 conditions for the market is identical to this one except for the set. So if set is 0, so they are identical, there's no externality. If there's an externality, the social planner will adjust. So the consumption of good 1 down, which by artificially increasing price of good 1, and because production of this from A also down, less production.
Okay. And could we say that the market solution then is inefficient?
Exactly,
Yes,
yes.
it is, right?
Exactly.
Okay.
Market solution is inefficient. because it's not, it doesn't get separated efficient outcome. So
Right.
market solution is inefficient. Is inefficient. Now let's do a simple example. This one is a bit weird probably because of these minuses which then disappears. And let's do another one which is with consumption externality and only two consumers. Makes our life a bit easier. And now to change, we will do a positive externality instead of a negative one. Example 2. Here we have two consumers and two goods. The utilities will be as follows. Consumer A chooses XA and YA in this utility, depends positively on the consumption of consumer B's of X. For X3, what consumer 2 chooses to consume of X, enters utility A's, consumer A's utility positively. And UB is the standard one, so that is one without externality. So if you want to try any positive externality, by consumer A does. And the initial endowments are 1, 0, 1. Now we start the other way around. First we do competitive equilibrium, and then we do the efficient equilibrium. Very efficient conditions. Competitive equilibrium. Okay, so both consumers maximize utility. FOCs for consumer A. You get PX over PY equal to YA over X. There's a budget constraint. PX is defined with X is the market, and price X, and Y in the market is price Y, and he's selling the unit of X he has available. What we get from this, combining it, calculating it, you solve here for PXXA or PYYA, plug it in here, and then you get XA is 1/2, and YA is PX over PY 1/2. For consumer B, you get something similar. PX over PY is equal to YB over XB. And its budget constraint is PXB plus PY, YB is equal to PY. And here, because now PY is the initial endowment of the consumer, we get YB is equal to 1/2 by combining these two, and so PXXB XB is 1/2 times PY over PX. Then you do market clearing for one or the other good. Market clearing X. So you get XA plus XB is equal to 1, which is the total initial amount of the good in the market. So A's demand for the X is 1/2. Consumer B's is 1/2. Y over X is equal to 1, and we get Px is equal to Y, and both consumers consume half an unit of each of the two goods. Equal YA equal YB equal 1/2, and we see that The consumer passes the externality, consumer B by consuming X. They consume the same quantity, so here you could get a higher utility if consumer B was allowed to consume more of X and consumer A more of Y, because X benefits both of them. So consumer B should consume more of X and consumer A of Y. This is the logic behind the externality. And well, in the market outcomes, they don't do this. In the Pareto efficiency, we will find this. And the question is how to find the formula. Conditions for Pareto efficiency. Again, you can maximize the sum of the consumptions or one consumer's utility subject to the other getting a certain level. So this is how I do it here, equal to the upper bar, condition lambda. And then we have the two resource constraints, we have XA plus XP equal to 1. This gives me the raw constraint, and then a new constraint, which is the resource constraint for the Y utility. Amount of these two goods we can allocate per month to consumers. First of all, these have to be non-negative amounts, and second, the sum of X and Y has to be equal to 1. First order conditions. Well, Lagrangian, which is set to XA, YA, XB, A, XB here, minus, here it is, raw, equal to 0. Back to YA, XA, XP minus mu equal to 0, L, XP equals XA, YA, so XP is here, here, and here, plus lambda by E. Because this is the goods that causes the externality XP. We have consumer A's utility and consumer B's utility and the resource constraint here. We have 3 arguments in this order condition. And with respect to YB, we have again the standard one, lambda XP, consumer B's utility and the constraint here, minus the resource constraint. We combine these two, get a ratio of mu raw over mu. YA over XA, it will be this marginal rate of substitution from before. This we combine with this equation here, these two here, this one and this one, and here we get XA, YA, plus lambda YB, over XA, XP, raw and mu. Then we combine 2 and 4. And the XP is equal to mu. And this is all equal to this one. With equation 1, 2, 3, 4. So combining the second with the fourth condition, the both are equal to mu. XA, XP, equals at lambda equal to XA. And we plug it into here. And then we get, because the lambda then disappears, XA cancels out, YA over plus YB over XP, and YA over XA. Okay. This is equal to raw over mu. It is equal to 1 over XP. We also get from this 1 over XP from this condition here. condition tells me that the ratio of marginal, so how they have to consume it in this ratio, this is actually not identical to the one which I got in this markets condition, so this is 1/2. Because consumer B has to consume more in this outcome than output X, because it affects both consumers positively, the utility than consumer A. So 1/XP is equal to YA/XP, and so we have a more amount of XP for consumer of X or consumer B. This is not equal to the condition here, because here what we get is 1 divided by XP is 2, while YA/XA is 1, so this is not true in the market condition. So again, the market outcome is not efficient. Market outcome is efficient. Yes.
So why is the market outcome efficient?
Because you can compare this condition with the market outcome. 1/XP is 2, 1 divided by 1/2 is 2, and YA/XA is 1/2. Divided by 1/2 is 1. This condition, the market outcome is 2, 1 divided by 1/2, and this one, 1/2 divided by 1/2 is 1. This is a condition for efficiency, and it's not fulfilled in the market outcome.
Is that a specific reason why we started with the condition from the efficiency in the first example and then we did in the second? Like, can we start with one or the other, or is
It doesn't matter. You can maximize the sum of utilities. You can maximize the sum of the utility of one consumer, subject to the other consumer reaching a certain utility. It always gives you the same solution. Sometimes one procedure is easier than the other, but in the end with conditions. So what you put in the objective function, if you don't put it in the objective function, it goes into the constraint, so it doesn't matter. You capture it in most ways. Well, over time you either get a feeling to what to do, or what to do best, or if not, you find one way to do it always like this, with the dotted line. So in the end, you always arrive at the same solution, one way or another. Because they're equivalent. So this was the externality part. So you see that the evaluation outcome, it was very nice in chapter 5 with the welfare theorems. With externalities, it doesn't hold. And now we do the second example where it doesn't hold, which is public goods. If you have public goods, it doesn't hold either. So what are public goods? Public goods is like the sun, which it's non-rival and non-exclusive. So the first thing is I cannot exclude anyone from consuming it, because if I consume it, somebody else can consume it. And it's not rival. If I consume the sun, by lying in the sun, somebody else produces solar power from the sun. Agriculture uses the sun to produce some food, some wheat or whatever. It doesn't diminish any of our utilities or productivities. By if one house uses it, the other one can use it as well. You get the same benefit from this public good. So the main characteristic of a public good is that it's non-rival. Public goods are non-rival and non-exclusive. You can also think about this like a multilateral externality. Multilateral externality. Which means public goods, and some of them are a bit borderline because good, or think about a public swimming pool or a public library. They are in some sense public goods because they are non-rival and non-exclusive, to a point. If you have too many people in the library or the swimming pool, it's rival, but in principle it's non-exclusive and non-rival because it's public, so someone pays for it, and then the one providing it creates this multilateral externality in terms of the first part of this chapter. And then what we get is, well, if you privately obtain okay, let's see, Pareto optimal allocation for public goods. Pareto optimal provision of a public good. Well, maximize by choosing X sum of utilities for the consumers, do I of X minus C of X, because one consumer, if once it's provided once, it's paid for once, everybody enjoys it. So the Pareto efficient outcome is the optimal provision of the public good is equal to the marginal sum of marginal utilities. This the sum of the marginal utilities, I prime X, is equal to C prime X. And this is called Samuelson's condition. It's from Paul Samuelson in 1954-55, almost 75 years ago. So the sum of the consumer's marginal benefits from the public good should equal the marginal cost. So I sum all the marginal utilities of all the consumers and set them equal to the marginal provision of the cost of provision of the public good is my optimal solution. When there's no social planner, somebody providing this public good, we get a free rider problem. Each consumer wants to enjoy the public good, but prefers that someone else provides it. Okay. Without social planner, or the state, or some generous philanthropist, a free rider problem exists. Each consumer wants to consume the public good. But prefers that someone else provides it. But private provision of the public good is inefficient because you only get up to the point where what is the private provision of the public good? Private provision of the public good is inefficient. What you do, each consumer maximizes individually this thing, so each obtains a first order condition, which is U I prime x equal to C prime x. And so what we get is that only the consumers that values the public goods the most, whom this marginal utility is valued the smallest, is providing this public good up to this C prime x. So only the consumer who values the public good most an example.
What does that last phrase mean? When a consumer provides the amount of public good provides it and
So
all.
because now it becomes a private good, since it's private provision of the public good, it essentially becomes like a private good. So it's provided, the nature of the good doesn't change, it's public, everybody can consume it, but only the guy who's like, has the more highest willingness to pay for it, pays much utility, pays for it. Everybody else doesn't.
So we're assuming, in that case, we're assuming everyone knows how much utility each one of us gets from the public good. Because
This is
if
not
not,
strategic.
then
No, I could say I will use the public good the most, but I'm strategic, so wait, maybe somebody else provides it.
yeah, that's what I was thinking. So at the end, I thought no one provided it.
Exactly, because we all wait that the other doesn't. So in some
Right.
sense, here we know everything is common knowledge, there's no strategy, no strategic behavior, so you know the other's valuation is probably good, you know you are the one who values it most, so if you don't provide it, nobody else will provide it, and everybody else knows since you value it the most, you will provide it. So the not the strategic here in consideration. And now we do an example, this is again one of these textbooks examples. Suppose there are two students who share a flat, and then we will see whether they want to live together or not, because then they can share the square meters they are buying of this flat, or they live in separate places or separate rooms. So this is consumers A and B, with the following utility. So X is square meters of flat, and Y is other consumption, and this is a public good, so there's no index of the consumer. But by I there's an index of the consumer because it's other consumption. And so we have I equals A and B. This is different for the two consumers. The X which each of them buys goes into this common pool, and both of them enjoy X. Suppose that you have a monthly income, which is not realistic, 3,000. But like this, the numbers work, 3,000. And your prices of X is 100, but I didn't specify currency. It's going to be, and Y is 2. It's going to be a different currency, drops to actually 20 cents. So each of the students A and B has 3,000 euros or 3,000 bucks. Monetary units, price is 100 of X, and Y is dot 2. Okay, what is the optimal outcome living alone? So individual utility maximization, which is essentially equivalent to living alone. So you don't share a flat, living alone, no sharing of the flat. Well, each consumer maximizes. X elevated to 1/3, Y elevated to 2/3, which is utility, it's a Douglas utility. Subject to the budget constraint, 100x plus per 2y equal to 3,000. And then we get first order conditions, marginal rate of substitution, which is 1/2 y over x, is equal to the price ratio, which is 100 divided by log 2, 500. From this we get y is equal to, multiply here, 1000x. And then from this we get, with the budget constraint, so plug this into the budget constraint, and then you get into what we put in here, then you get x is equal to 10, and y is equal to 10,000. This is individually living by yourself, this is how much you buy of x. Then we have B. B will be the two consumers share the flat, but they decide basically each of them how much to provide, which will be the mesh equilibrium, the non-cooperative solution, and part C will be the social planner. If you have a social planner, how much you the social planner would provide to maximize the sum of the utilities. Okay. So now they live together, living alone, individual utility maximization. Now they share a flat. Share a flat. So what you do is, but maximize utility individually.
Sorry, what it says that
They share a flat.
sure.
Share. They share the flat, but they maximize the utility individually. So you don't basically best reply. You get like a Coulomb equilibrium. So now you don't have any more the consumption of X here because you are providing now your XA as consumer A and your XB as consumer B, and you sum this. Before you consumed it individually, so you only had the X in there without superscript because it's the same. But now both consumers contribute to this flat and they consume what both of them contribute. This is a public. Here's no public. Now we have a public. The budget constraint is unchanged because you still have the same amount of money which you spend on the two goods, just that good X is now shared. Okay. Get the first order condition. I 1000 is the same as before, just that X is now XA plus XB. And with the budget constraint, plug it into the budget constraint. So you divide again by dot 5 into DC in here. You get 100 XA plus 200 XA plus XB with 3000. And then basically solve for, because we maximize consumer A's utility first, provide A, we solve for XA, and if you solve for XA, you get this n 2/3 XB, and this is like this Coulomb best reply function. So depending on what XB does, how many square meters XB provides, XA provides this amount of square meters as a best reply to XB, which we see actually in chapter 10. In chapter 8, it's the Nash equilibrium, but like this. And YA is equal to, and this you get from here, for example, 10,000 times, that is in here, 10 plus XB third. Then you get the intersection of these two best replies, which is essentially the Nash equilibrium. I go back to that. Intersection of best replies, which later on you will get to know as Nash equilibrium. So I plug the XB1 into the XA1. So I plug XB is equal to 10 minus 2/3 XA into XA. And get XA is 10 minus 2/3. And here the XB comes in. And instead of XB I put this here. 10 minus 2/3 XA. You solve. 5/9 XA. As with your 1, here you get minus 2/3 times 2/3. Minus 2/3 is plus 4/9. 9/9 minus 4/9 is 5/9 on the left hand side. And on the right hand side we have this 10 minus 2/3 of 10, which is 6.6. So the left is 3/1/3. XA is equal to XB is equal to 6. Okay? So each of them buys 6 units of the flat. Before they were living at 10 square meters, now they get 12 square meters.
So that's 5 over
9.
X8, right?
Mm-hmm. And y is equal to yb from the previous condition. You guess this goes up to 12,000, so more private good consumption. What does the social planner do? We can already anticipate the social planner will probably want to consume even more public good. So the social planner maximizes the sum of utilities for the two consumers, or one consumer's utility subject to another. Here what I do is I maximize the sum of utilities. Maximize x 1/3, because now the consumer x is not anymore chosen by the consumer, so the social planner chooses X for both of them, and the private consumption goods, YA and YB. Subject to the budget constraint, which is 100x plus the 2 YA plus YB equal to 6,000, because now the social planner has the entire amount of money of the two consumers. That's the gross over conditions with respect to x, y, a, y, b. With respect to x's, 1/3, x minus 2/3, y, a, 2/3. Last 1/3, x minus 2/3, y, b, 2/3. And then we have the budget constraint here, that's the lambda. So this gets a lambda. The second one with respect to YA, and the third one with respect to YB will be the same, but let's split. YA, we have only the first part. Then x plus 1/3. And from the constraint, minus 2 lambda equal to 0. And here we get 2/3 YB, elevated to 1/3, x 1/3. 2 number equal to 0. And then you see, as expected, that the two consumers will get the same amount of private good consumption as before in both cases. You get YA is equal to YB. This we would like into this condition. And then we get, for example, 1 and 2 together, 1 divided by 2. We get 1/3, x minus 2/3, YA 2/3, plus 1/3, x minus 2/3, YA 2/3, because YA is equal to YB, divided by condition 2, which is 2/3, x 1/3, YA minus 1/3, and this is equal divided by 100 over 2. And here what we get is, because all the a's cancel out, by a's cancel out everywhere. No, sorry, they don't cancel out completely. So they do not cancel out completely. But we get 1/2, because here we get this 1/3 divided by 2/3. So it becomes a 1/2. And here we get 2 YA elevated to 2/3, and then this goes up, so we have 2 YA, so plus 1/3 goes up, so 2/3 plus 1/3 is 1, the exponent disappears, and down there we get the x 2/3 go down, with the 1/3 here becomes a 1/2. This is equal to 500. So we have YA, this one take away. YA is equal to YB, equal to 500x. This will plug into the budget constraint here. Where is it? Subject to budget constraint here. And then you get x is equal to 20, and so ya and yb is equal to 10,000. So they can consume more public good because the sum of utilities is larger and less private goods, and if they individually choose the optimal amount of good X, which is a public good, how much to contribute to. Okay, you see, so the market solution is inefficient. One last thing on public good. Like the EU tax, we have something equivalent in terms of this contribution, and this is called Lindahl taxes or prices. Maybe you've heard about this. Swedish economist, Lindahl taxes or prices. So if you cannot impose a social blender solution, what you should do is, okay, to restore rate efficiency. In a competitive market. Lindahl proposes so to restore Pareto efficiency in a competitive market, Lindahl proposed to charge personalized prices. Maybe to use a personal price per unit of public good. Public good that is equal to the consumer's marginal utility. One moment. Also public good. Okay. No.
I was gonna ask, I think you don't apply this here in Europe, but have you heard of that stratification in countries? Are they doing the income tax pricing with that?
I'm not sure what I drink some of it, but I'm not sure what it is exactly. So, what is it?
Depending on where you live, and they give you like a number of, like a state of network you have from 1 to 6 in Colombia that applies. And if you live in certain zones, you can pay like 5 or 6 times more for the electricity than people in other zones.
Because you're rich.
Yeah, exactly.
This is something like this. But so what you do is, instead of having personalized prices, what you do price zooms. When you put together, you
Cluster.
clustering of consumers in different income groups according to where they live, and then you live in a place where you are supposed to be richer.
But that sounds like income tax.
Yeah, like the income tax.
But then the incentive, what you create is that if you are in the zone with the highest price, you move to a different zone where the price is lower. And then you pretend to be poorer by moving to a different zone.
Yeah, that's happening in Colombia. So.
Exactly.
That's a bad top soup. You start not declaring or
Or you don't declare your taxes.
Exactly.
And then you keep living in the same area, pretend to be poorer, so your average income in this area goes down, so you don't declare. One of them is always the problem is how do you make people reveal the true valuation of the public good, is what Mr. Rad asked. So in principle, well, how much do you want to pay for the public good? Well, I pay nothing, I want the free ride. Somebody else should pay it. This is what other people do. And how do you do it? Well, it's difficult because it's very different. First of all, incomes are different, and it makes a difference whether you have different incomes. You get a very different solutions, and if valuation of the market of the public good are different. This I've done with a course in a network setting, in social network setting, and we see that the outcome is very, very different if the demand of the public good is driven by richer consumers demand more public good because they demand more of everything because they're richer, or some consumers which have the same wealth value the public good more. So you get a very different outcome. And so it's not easy to do this in reality. And from the terms of the, like what you observe is, as an econometrician in some sense, you have some consumers which demand more public good, but you don't know why. If you don't know why, because you don't know the valuations, incomes you can observe quickly, but the valuations you cannot. You don't know if this is driven only by incomes, or also, or only by valuation. And since you cannot observe this, you don't know. Okay, so this is chapter 6. And next chapter, next time we will stop writing a board. For me, it's something which I'm always, when I started 2008 to teach this subject, I was teaching different, the content changed. Game theory was not taught then. Some of the content which is not anymore important is out, so I did more stuff that is boring. Now we do less stuff than this then. I wrote everything on the board for 10 years or so. Then I started switching to slides. The good thing about slides is it's less intense for you, but then I'm going much faster because slides I don't need to write on the board, but I can click through the slides and go much faster. The good thing about the board is because you have to focus on these specific things, the small details. If I don't do a mistake, when you read my handwriting, it's better than you copy it because like this you are more aware of these small details and differences. So for all these theoretical part, I think it's good that I do it on the board instead. Because I've shown you a picture of some of these general equilibrium outcomes, you see how it looks like. But since you didn't draw it, and you didn't see me drawing it, it's probably not easy to, so you better understand it if you draw it yourself. But okay. Some students have me now, I want slides on it. But okay, I still think I'm a bit slower with the board, which is useful for you guys, and you have to draw it. It's also useful for you, so if you want to draw it or write it down. But I think this is good, but this is my opinion. So next week you see how it works with the slides. There will be chapter 7 which is left, which is on, so we will put this, and this is why I did uncertainty in chapter 2. We will put all this general equilibrium setting with uncertainty, and this will capture financial markets. So we can also use financial markets as a general equilibrium model, and you will see how this looks like, because we will have uncertainty and so on. We will sell stuff because the uncertainty is reduced. Now you buy shares, tomorrow sells a profit, so we will know how it will look like. And then chapter 8 will be game theory, which will be the basis for a lot of IO stuff. Next semester we have industrial organization, and for this you need game theory. So there are some guys which have me in game theory in undergrad, will see that this is similar. You will be lucky, because more or less the same thing. There's a difference that instead of taking 3 months, we will take 2 lectures. Each not the same, but a bit less, but half the content. 1.5 months include lectures, plus level will be higher, so the exercises will be a bit more challenging. Okay. We see next week on Friday. So have a good week, good weekend, and see you next week.
Thank you.
And if you need help with the problems or anything, you can still write to me. So nobody who came to office hours yet. So if you need it at some point in time, let me know. Okay?
Bye.
Welcome. See you.
See you.
Bye.